Good morning, everybody. So today we will continue with our algebraic spectral studies. Right? Yesterday we did about Laplacian spectrum of various classes of graphs, right? And also some special cases we saw when the matrix takes a very particular form, then how can we compute the Laplacian spectrum, right? So computing Laplacian spectrum we have seen. Today we will go further into it, we will see some more properties. Okay, so before we go into Laplacian spectrum, I just want to digress a little bit and we will go back to the incidence matrix that we have been looking at, because that would help me to touch upon Laplacian matrix. So we saw about the incidence matrix, right, Q of G for directed graphs. At least I gave the definition for directed graphs. We will then see if it is 0, 1 or undirected graph, then how this is going to change, right. So we had defined already that this is going to be equal to 1 if at any ijth entry q of ij is going to be nothing but 1 if the vertex ui is incident with the edge Ej, right, or I could say the edge Ej is incident with ui, and we also saw -1 if it was I mean here when I meant incident, I just mean that ui is the tail end, that is ui, the edge Ej originates from ui, right. So we are talking about directed edges. So if this is the case, then I say if ui uj is this, let me just use a different notation, say ui uk, and if ej is the edge we are talking about, if in this direction, then I am telling you that the entry qij, right, the ijth entry of this matrix is going to be equal to 1 for because ui is the tail end of the directed edge, and the corresponding k would be taking -1 the other end, right, because it is an incoming edge. So this would be -n 0, and if ui is not incident on ej at any end, then we write it as the entry would be 0, right, and this would be otherwise. Okay. So this is the definition that we have seen with respect to directed edges, directed graph. So now I just want to look into the column space of this. We know this is an n by m matrix, right. If there are n vertices and m edges, then Q is nothing but a matrix of order n by m, right. N rows are there, each row corresponds to my vertices, and m is going to be number of columns, which is the number of edges, right. So this we have seen. So what can we say about the column space of this Qj? So we have already seen that rank of this matrix is n minus 1, right, at least n minus 1, sorry, at most n minus 1, depending on whether our graph is connected or not. This would be n minus 1 or n minus k, depending on the number of components, right. This much we have seen already. So now my question is, when I say n minus 1, what would be the column space? We know every column adds up to 0, right, because if I look at an edge will always have an tail end and front end. So it will be 1 and -1 will be there. So column sum is going to become 0, right. So the idea is, when I go into the rank space, I want to look at the vectors, because now we want to talk about the eigenvectors. We know if 0 is the eigenvalue, we have also seen how my eigenvector is going to look like, right. If lambda equal to 0 is an eigenvalue of this Q. Let us look at the even though it is a rectangular matrix, we will talk about the square submatrix, and we are talking about that. So what am I then what do we know about x in this case? We know each component is going to be equal, right. The vector is all one's vector, right. This we have already seen. Now my question is, this is about 0 eigenvector, right. If 0 is an eigenvector of my matrix, or the Laplacian also, there we have said. Now my question is, if I say rank of Q is at most n minus 1, what can I say about the column vectors of this Q matrix? The column space. Okay, I just digressed here talking about eigenvalues, and obviously we talk eigenvalues for square matrices, but I am just giving you a small hint here to connect it over here. Okay. So, the idea is the Q matrix, the range space, if we are looking at the range space or the rank, since rank is n minus 1, then we know that there are suppose let me take connected graph itself. So, let us fix this to be equal to n minus 1. So, that means what? There are n minus 1 vectors, column vectors, right, which would span my range space. Right? That is what I am trying to say. By spanning, what do we mean? We take any linear combination of these n minus 1 vectors, I will get all possible vectors that would belong to my range space of this Q. Right. So, how are my vectors going to be looking like? What are the possibilities for my vectors? So, the idea is that if you look at any vector, since we know the column vectors all sum up to 0, so that is the only thing that we have to catch hold of, right. So, my range space is going to contain vectors of the form, it will contain all vectors of the form whose sum, the sum of the components is 0, right. Because if I look at any n columns, I know it is going to span my space, right. So, that means what, every column is going to add up to 0 here. So, if I take linear combination of any of this, it will again add up to 0, right. So, that is the idea here. So, so the result what we want to talk about is, suppose G is a connected graph, maybe I will just write that statement here. Say let G be a connected graph on n vertices, then the column space. So, now I am not using any other language, I am just sticking to this column space of Q of G, the matrix which we have defined already, okay, consists of all vectors x in the n dimensional space, okay, such that sigma x I is equal to 0. So, I equal to 1 to n. So, what is this x I? So, x I just need to write this as x 1, x 2, x n. So, how do we prove this? Because when I say a statement, we are trying to always prove it. So, how do I prove this? So, there are two things now with us. We have the matrix Q and we are now talking about the column space of Q, and we have a space in Rn where sum of all the vectors, the subset where every vector has the sum of its components being 0. Right? We are talking about two things, and I am just trying to tell you that both of these are equal. Right? So, how do we show that this is equal? I mean, it is very simple basic linear algebra that we want to use, we will not use big thing. So, suppose let us start with it. I want to show that the space is equal to this set of all vectors is 0, right. So, let me just take, let W be the set of all vectors in Rn such that the summation xi is 0, they are the component sum of its components is 0. Right. So, let us also start with, let U be the column space of Q. Okay. I am just claiming that this U is equal to W. Right. So, what can we say about this rank of W? Yes? Dimension, sorry, did I mean rank? Oh, I am sorry, I am talking about dimension. Thank you. Yeah. So, dimension of the space, if you see what is the dimension? you have n elements, right, every vector has n elements, and we are giving you a relation, you add them all, it vanishes. So, that means what? I can write like any one vector as linear combination of the remaining n minus 1 vectors, right. So, therefore, we can immediately see that dimension of this space is equal to n minus 1, right. So, now coming to U, what can we say about U? We have already seen the dimension. Sorry, here also I think I was trying to write about dimension, I was talking about rank. Yeah. So, coming back here, so what do we know about our space U, connecting it to Q? We know that every column in the column space of Q, every vector adds up to 0, right. It is a very trivial vector which is like 0 0 1 0 minus 1 0 like this, right. It is a kind of columns which would be like this, right, which would look like this. So, now we can immediately say that all these vectors of U are going to be subset of W, because every column in the U has to be, will sum up to 0. It only has 1 and minus 1, that is the restriction that we are talking about here, right. So, we can immediately say that U is a subset of W, right, and we know dimension of W is n minus 1. What about dimension of U? Since we know Q is already its rank is n minus 1, so dimension is also n minus 1 there, right. Rank equal to n minus 1 means dimension of the range space is also n minus 1. So, therefore, we can simply say that n minus 1 is equal to dimension of U, right. When we have a subset, what do we mean? We know that this cannot go beyond dimension of W, right, and we also know this is going to be equal to n minus 1 on the other side, right. Dimension of W is n minus 1, dimension of U is n minus 1, and U is a subset of W, which means trivially it has to be this improper subset, which is nothing but U is equal to W, right. So, we will be using this idea again when we are going to prove our later results. So, just for that only I gave the requirement of linear algebra here. So, we will go into the next result. You would have all seen in the assignment sheet, problem sheet, that we spoke something about totally unimodular, right. What was that definition? A matrix is said to be totally unimodular if the determinant of that matrix is 0, plus 1 or minus 1, only one of these three can be occurring, right. In fact, it is not just the determinant of the matrix, we are talking about determinant of every submatrix. Every submatrix in that will have a determinant 0, plus or minus 1, right. If the determinant of any square submatrix, so this is where we are going to use determinant. Obviously, we need to talk about determinant for a square matrix. So, determinant of any square submatrix is 0 or plus or minus 1, plus 1 or minus 1. Okay. So, now the claim is this matrix Q of G, whatever we have, the incidence matrix we are talking about, it is unimodular, totally unimodular in fact. Okay. So, if G is a, this is the next result, Q of G of any graph G is totally unimodular. So, how do we prove this, or what should we prove here? To show totally unimodular, what should I show? Yes? Product of 1? Yes? I mean the definition is right above. It's a statement which says for any, right? It's a statement for any square submatrix. That means what? We have to show that every square submatrix is going to have the determinant 0, 1 or minus 1. and I am giving you Q of G, the incidence matrix, right. Q of G is the incidence matrix we are talking about. So, how do we show this? So, one thing what we can see is, obviously we are talking about any square submatrix, and we know that Q of G has rank, what to say, if I look at the dimension of it, it is n minus 1. So, if I look at any n by n square submatrix, it is an n by m matrix. So, if I look at any n by n square submatrix, what will I get the determinant? 0, right. It is a singular matrix if we look at it, because every column sum is going to be 0. Any square submatrix, if I look at the n by n square submatrix, it is 0. That is one clear part that we have. So, now I want to show this is going to be true for any submatrix that I take inside this. So, is there any proof that we can think of? How can we prove this? So, when we mean any square submatrix, we are telling k by k square matrix, right, for every k lying between 1 and n. Not necessarily, right. What if you take a column, say suppose I just look at this, something like this. If I look at this square submatrix, will this be an incidence matrix? 1 is there, but where is the tail end for it? I mean, we are talking about directed graph, let us even fix to directed graph, later we will go into 0 1 matrix. So, in this case the result is very particular for this definition of incidence matrix. Okay. So, in this case obviously it is not an incidence matrix, even though it is identity matrix we know, but it is not an incidence matrix for some graph, subgraph also. Okay. So, let us look at, let us go by induction. As discrete mathematics people, we always love induction and contradiction, right. So, let us start with induction. I know at least for n, k equal to n, I know upper bound, but still we will prove that also. So, let me start from the basic case, k equal to 1. What about any 1 by 1 submatrix here? It has entries only 0 or 1 or minus 1. So, determinant of that is going to be equal to 0, 1 or minus 1, right. So, when k is equal to 1, I can simply say that determinant of this, I will just write it as qk to mean that k by k submatrix. Okay, whatever submatrix here we are talking about, if we want then we can talk about the set I and j and all. So, now we do not want to complicate the notation. So, let me just think about this. When k equal to 1, we have 0 plus or minus 1 as the entries. So, any 1 by 1 entry has this. So, we can immediately conclude here. So, now by induction, if I go to the second level k equal to 2, if I look at any 2 by 2 matrix, what are the possibilities for my determinant? So, if suppose I look at any 2 by 2 matrix, if my column sum there also, if it adds up to 0, every column sum is going to add up to 0, then what do I know? I mean, we have only 2 by 2 matrices possible, like 1 minus 1 minus 1 1 or 1 minus 1 1 minus 1, then column sum has to become 0 or all 4 entries are 0, right. So, these are the only possibilities when my k is equal to 2, right. For the 2 by 2 matrices can be of this form, right, 1 minus 1 minus 1 1 0 0. In all these cases column sum is 0, determinant also becomes 0 here, right. So, in all these cases determinant is 0. What are the other left out possibilities? I will have 1 0 0 1, 0 1 1 0 or minus 1 0 0 minus 1 or 0 minus 1 minus 1 0. And these are the other possibilities for my 2 by 2 entries. I have just written it down. Technically also you can see that if I want to extend this argument, okay, first let me finish this. So, in each of these cases, what is the determinant? So, in these cases I will see this is determinant is 1, for this it is minus 1, here it is 1, this is again minus 1, right. So, we can see that any 2 by 2 submatrix is going to have determinant again 0, 1 or minus 1. Okay. So, inductively now I can proceed. Think of a k by k matrix, right. If the k by k matrix has every column of the k by k matrix adds up to 0, then I can immediately conclude that the determinant of that is going to be 0, right. So, in that case what happens? The columns contain, like, either the columns are all zeros or it contains 1 and minus 1 both paired in, right. So, only in that case you will get determinant to be 0. So, what is the other possibility? Every column contains at least one non-zero entry, exactly, or I should not say at least, exactly one non-zero entry, right. If that is the case, then we can see that you just look into this k by k matrix, right, and I am saying that there is some column whose sum is not equal to 0, right. Pick out that column, right, and what will happen to if you just replace this column by sum of all, I mean we are talking about this k by k submatrix, pick out all these k columns, k rows, right, we are talking about submatrix, square submatrix, k columns and k rows. If I add all these rows and replace this particular column whichever was not vanishing, what will we get? Or should I say row instead of column, I can just say row wise also, yeah. So, since this column does not vanish, let me look at this last column, right. So, what will happen if I add all the row and replace the last row, the kth row, if I replace by sum of all the k minus 1 rows, yeah. 1 0 0, I do not know, I did not tell you what this entry is here, right. I am talking about this last row, it could have the possibilities are it can have 1 0 minus 1, all the 3 possibilities are there, right. If it is 0, then if my column sum adds up to 0, then I know if I add these rows I will get a 0 entry here. If suppose this was a 1 and my column adds up to 0, that means there was somewhere else a minus 1, right. So, if I add these rows, then I will get minus 1 here, right. So, in this sense what I am trying to tell you is this kth row will be nothing but I mean if I add all these R1 plus R2 plus Rk minus 1 and replace it with in Rk, this would be nothing but this sum is going to be nothing but negative of Rk. If it was plus 1, the sum of the rows would give me if it gives me plus 1, that means what, there was a minus 1 here which had killed this column, right. If it was minus 1, then there was a 1 here which would have killed the column. If there is at least one non-zero row, I can just catch hold of this and I can say this is going to be of negative of that row. So, what happens is if suppose I replace this column by this, what will happen? My determinant say of this matrix I will call it by x and this replaced row if I call it as y, the matrix y, then my determinant of x is going to be nothing but negative of the determinant of y, right, because the last row is negative of itself. Now, I have replaced it by sum of all the rows and I am replacing it there. So, that would give me nothing but determinant of y would be negative of determinant of x. There is a sign change happening over there. So, you will have this quantity. So, what does this tell you? If determinant of x is 0, determinant of y is 0, right. If determinant of x is not 0, that means I obviously determinant of y is also non-zero, but what value will it take? So, we are talking in terms of induction, right. So, this determinant of this matrix would be like from the lower order level, if you pull it out, it would be either plus or minus 1 or 0. So, I can just extend it, if I expand this along any one of this element in the row, maybe this non-zero entry in the row, I will just get the determinant to be 1 or minus 1 or 0. Okay. So, this is an argument we will be like most of the time using, like you just add all the rows and you try to look at the behavior of this determinant. Okay. So, this inductively if I continue this, I can show this for every k up to n. So, therefore, we can say that q of g is totally unimodular. Okay. So, this is what I wanted to show. So, q of g is totally unimodular. Okay. Actually, this result, the beauty of this result is we will extend the similar property to Laplacian matrices also, and this idea of unimodular also finds applications when you are trying to solve an integer linear programming problem, right. This matrix has the determinant only 0, 1 or minus 1, and we know when this happens, especially when I connect it with my graph, right. I have a incidence matrix. So, if I look at such a matrix, if I want to convert an general linear programming, solve an integer linear programming from there, right, because general linear program has a polynomial time solution, whereas integer problem does not have a polynomial time solution, right. So, in that case, can we use this? I am just throwing up an idea to you, can we use this to connect these kind of problems? Okay, so, you can think about it, because there are some ways of handling integer linear this unimodularity gives us a way where the determinant is 0, 1 or minus 1, tells you we are going to handle integers somewhere, right. So, can I look for maybe a 0, 1 solutions, possibility of 0, 1 solution of linear programming problem, right. So, you can think about it in this direction also, like can we have a transformation, or can you make a gadget which will convert your problem in through this to somewhere else, so that you can use the determinant of this and find the solution for the problem. Okay. So, this is again another technique that you could catch up with. Okay. In similar line, I will not give the proof, but I will just let you know. Suppose we have a tree, let G be a tree of order n. Okay. Then any submatrix of order n minus 1, okay, for q of g, of course, we are still in q of g, then any submatrix of order n minus 1 by n minus 1, square submatrix we are talking about, is non-singular. So, we know tree is connected, right. I am not talking about forest. So, I am talking about a tree. So, it is a connected acyclic graph on n vertices. Then if you look at any submatrix of order n minus 1, right, then we know the determinant has to be non-zero, because we will, if you look at the corresponding eigenvalue argument we did yesterday, you will be able to connect the dots, right. So, I will not give the proof runs in similar lines of the previous result that we spoke about. So, the idea is this n by n minus 1 by n minus 1 submatrix is non-singular, that means what, the determinant is non-zero for a tree. Okay. So, we will make use of this and we will jump into the Laplacian matrix now. Because I need this result, I will be using it in the later part. Okay. Suppose we have an unweighted graph, okay, unweighted, undirected, connected graph. Okay. So, this we will start, always we have this in mind, because parallel results are there for each of this terms that if I drop that, what will happen. So, I can talk about each of them in parallel, there is a lot of study, unweighted, undirected, simple graph. So, if I add direction to it, then the whole theory goes in a little bit different way, because you do not have symmetric matrix, it becomes skew symmetric or non-symmetric, right. depending on how you want to define directions and edges and the matrices, right. Or if I want to talk about weights in my graph, because as we include weights for edges, my matrix becomes from, I mean it transforms from 0, 1 to any real matrix, right, if I am adding a real weights to it. And then it becomes a generic case of handling a generic symmetric matrix in case of weighted undirected graph, right. So, each of this terminology is important, so that is why we do not miss it. Every time we define, we restate it again and again. So, just for you to remember. Okay. So, let us keep it simple, undirected, unweighted graph. So, in fact, even I do not want to allow at this point of time any loops or multiple edges also. You can also do a study of all these properties, spectral properties in each of those cases also possible. So, yesterday we saw something about cofactors, right. I hope you people remember it. So, for a Laplacian matrix, we said that the cofactor of any two elements in the matrix is equal, right. They take the same value. Right, that is what we had stated yesterday. So, today I will just go back to it. What is a cofactor? Again, determinant of n minus 1 by n minus 1 submatrix, right. So, connecting this with our previous result for Q of G, I know L is nothing but Q into Q transpose, right. Even though we define this Q for directed graph, you will see that when I take Q into Q transpose, it is going to be the Laplacian of the undirected, the underlying undirected graph. Okay. So, that is the idea why we write this Q into Q transpose. Okay. So, keeping this in mind and the previous result, I can just immediately conclude that